Hi, my name is Victor and I'll present my work with Professor Helio Pegado on panel flutter analysis with NASTRAN for composite laminated plates. We'll pass through an introduction about what is and how relevant is the panel flutter, an overview of the NASTRAN aeroelastic capabilities, the analysis procedure, and the results, discussion, and conclusion of our work. So, what is the panel flutter? The panel flutter is a dynamic aeroelastic effect that happens on skins or panels of aerospace vehicles subjected to high-speed flows, which is a coupling between aerodynamic, elastic, and inertial forces under supersonic and hypersonic flow passing above a panel that has an empty span underneath. It's similar to the classical lifting surface flutter, in the sense that it is an aeroelastic instability, meaning that at a given condition the oscillation amplitude diverges. However, this exponential growth at a critical condition is usually limited by nonlinear effects, and it becomes a denominated limited cycle oscillation, or LCO. And how relevant it is? The first report of the phenomenon was related to the failures of the V-2 rocket during the Second World War, but it has been mentioned in the development of several aerospace vehicles such as the North American X-15 in the late 50s and the Titan II rocket. And with the recent growth of the aerospace industry, re-entry, high-altitude and high-speed vehicles are becoming prominent. And the flutter is a design concern of those vehicles, such as the Space Shuttle, the Concorde, or the new design of the Lockheed X-59, or the Brazilian scramjet, the 14X of the Institute of Advanced Studies. And finally, how can we predict it? So, wind tunnel testing and flight test is a way, but usually too expensive and complex. The usual method is to model and simulate it mathematically and numerically. The study of the governing partial derivative equations has several approaches, including linear and nonlinear. Aerodynamically, it can be modeled with compressible potential flow, or more specific theories such as the Piston theory or the free molecular flow, with good precision and low computational cost. In the literature, it is also found to use CFD, but with great additional computational cost. And the structure can use the basic linear elastic equations or the linear von Karman large displacement theory. For solution of those equations, several methods can be employed, including the finite element method and the assumed shape method, or the exact solutions when possible. In this work, we will utilize the finite element method, the linear elastic theory, and the third-order piston theory. And what is the piston theory? Under high numbers of Mach and for small variations of angle of attack, a supersonic flow can be modeled based on its vertical speed for its normal wash, and its pressure can be modeled as an isentropic compression. This gives a one-variable function for the pressure given the vertical velocity of the piston, yielding the name piston theory. And we utilize the NASTRAN as our main tool of aeroelastic analysis, as it has great academic and industrial utilization in the aerospace sector. We will review the capabilities of aerodynamic modeling, aerostructure interpolation, and solution of methods for flutter. NASTRAN has 4 supersonic theories. The first 3 are based on potential flow and has a validity up to Mach 3. The piston theory, however, has a validity of from Mach 2.5 up to Mach 7. To interpolate the forces to the structure and the structural displacements to the aerodynamic mesh, NASTRAN offers 2 principal kinds of interpolation: the linear splines for high aspect ratio structures and the surface splines for low aspect ratio structures. And for the flutter solution, NASTRAN offers 2 classical methods with optional, more modern configurations. First is the K method, the American method, and the PK method, which is the British method. So, to complete our objective, we modeled the problem in NASTRAN, realized the mesh converse procedure, and then proceeded with the analysis of the laminated composite plate. We modeled a simple support square plate utilizing the NASTRAN aerodynamic element that has an element with strips of sub-elements, and to achieve significant model representativeness, those elements must be placed side by side to represent a single panel. At this point, a linear spline in each element is used, connecting the adjacent structural nodes. The PK method is used, and the result is computed with the adimensional dynamic pressure parameter, commonly found in the literature. One problem encountered was the complexity in the input of the NASTRAN aerodynamic elements. For this, it was developed an open source software to generate the NASTRAN book card. Next, we made a mesh convergence study where we found that the convergence of the first frequencies had great impact in the overall convergence, which is expected given the nature of the elastic Flutter solution that utilizes generalized model coordinates. It was found that a 20 by 20 mesh was most suitable. Finally, a laminated composite plate was analyzed, varying the orientation angle to obtain the critical Flutter critical conditions. The resulted analysis agrees with the literature with errors of less than 5%, but always with non-conservative values. So, in this work, we found that the development methodology is suitable for laminated composite plates, and a mesh with a minimum of 20 elements in each side is desirable to maintain model representativeness. Future works can include more complex configurations, different boundary conditions, materials, and geometries, implementing structural nonlinearities, or adding thermocoupling effects. Thank you for your time. I hope you enjoyed the presentation, and if you have any questions, I'll be happy to answer.